Let's look at an example where we apply Bernoulli's equation to flow through a pipe which has a change in diameter. We want to use the equation to see how the pressure changes as the flow passes from the larger to the smaller diameter. And if we put all of the static pressure terms on one side, we get this equation for the change in pressure. If we assume that the fluid is incompressible, the mass flow rate at points 1 and 2 must be equal. This gives us what's called the continuity equation, which is just a statement of the conservation of mass. Mass flow rate is equal to the product of the fluid density, the pipe cross-sectional area, and the fluid velocity. So we can rearrange the continuity equation to obtain an equation for the velocity at point 2. The cross-sectional area, A2, is smaller than A1, which means that the velocity of the flow increases as it passes into the smaller diameter pipe. By substituting this equation for V2 into Bernoulli's equation, we can see that since the velocity increases between points 1 and 2, the pressure between both points must decrease. This concept that for horizontal flow an increase in fluid velocity must be accompanied by a decrease in pressure is one way of formulating what we call Bernoulli's principle. It can seem counterintuitive because people often expect an increase in velocity to result in a corresponding increase in pressure. But it makes sense if we think about the conservation of energy. The energy required to increase the fluid velocity comes at the expense of the static pressure energy.